rules. My name is Michael Molina. I'm the Workforce Development Coordinator at SPTC and librarian for Oklahoma Transportation Library, and I'll be moderating this discussion. There will be a chance for Q&A afterwards. Please make sure you are muted during the presenter's presentation and also your camera turned off out of respect for our presenters. At the end of the presentation, you'll get a chance to ask your question. You can either type it in the chat or raise your hand and ask the person individually through your microphone. But again, please save questions for after the presentation. We will be sending out professional development hours if you need those, probably within a week or two after this presentation. If you attended the full session, you'll get an hour. If it's less than an hour you've attended, we'll round up or down depending on how many minutes you stayed for the presentation. We'll also send a survey after this presentation to say how we did, how did everything go, and also suggest new topics for future presentations. We love to hear feedback about what you want to see in future webinar series. So without further ado, I'm going to go ahead and introduce our two presenters. The first presenter we have is Dr. Joan Lynam, the Program Chair for Chemical Engineering at Louisiana Tech University and the George and Jean Baldwin Professor. She'll describe her methods for converting waste biomass from food processing into products. She and her biomass team have worked with mayhaw jelly, wastes, hibiscus wastes, rice husks, sugarcane bagasse, and coffee silver skins. Using hydrothermal carbonization and deep eutectic solvents, these wastes can be converted lignin-rich materials for use in cement and asphalt. Other creative solutions are being investigated or have been found for these secondary agricultural residues that are already transported to processing centers. And our second presenter is Dr. Syed Ashik Ali. He's a research assistant professor in civil engineering at the University of Oklahoma. He received his PhD and master's degrees in civil engineering from the University of Oklahoma in 2021 and 2016, respectively. Also, he served as postdoctoral research associate at OU for 3 years. Dr. Ali has led a number of externally funded projects as PI and co-PI, and his research projects have been instrumental in enhancing mechanistic understanding of performance and distresses of asphalt pavements, as well as developing guidelines and specifications for the Oklahoma Department of Transportation. Also, he has disseminated his research findings through publishing in peer-reviewed journals and presenting at different national and international conferences. He has received several prestigious awards, including the University Gold Medal for the highest GPA in his civil engineering program, and he was named a DeLisi Fellow during his PhD study. So without further ado, I'd like to turn it over to Dr. Lynam.
All right, I believe Dr. Ali is going to share his screen and show us the slides.
Just give me 1 second.
All right.
Is it good?
That looks perfect. Thank you much, Dr. Ali. Well, you can go on to the next slide. I think we already have heard about all of this. So you can go on. I do want to acknowledge the Southern Plains Transportation Center and the U.S. Department of Transportation for funding this study, which was in ward number 69A355-234-8306, CY, LTU, OU, LSU-1. Don't we love to hear those sorts of things? I also want to acknowledge doctoral students Shen Hajla Selim of La Tech and Mohammed Herbasti at LSU. And I want to acknowledge our colleagues who worked on this study. Nazimuddin Waziuddin, who I usually call Wazi, in the Department of Civil Engineering at La Tech. Mustafa Isifwi from the Department of Civil and Environmental Engineering at Louisiana State University. My graduate student, Mohammed Rizal Islam in the Department of Chemical Engineering at La Tech, Nafiza Taranum in the Department of Micro Nano System Engineering at La Tech. Both of these two worked a lot on the slides, so we do really appreciate their help. We will also acknowledge Kenneth Hobson of the School of Civil Engineering and Environmental Science at Oklahoma University, Musharraf Zaman, also in that school at Oklahoma University. So without collaborators, nothing would happen, right? Okay, so you can go to the next slide. This is the overall idea of the slide. So basically, we have, instead of having crude oil asphalt binder as sourcing it, we're going to replace some of that with a more renewable and sustainable asphalt binder from rice husks. So to do that, we are doing hydrothermal caramelization, which just means we put rice husks and water together in a reactor, and coming out of it was sugar water from the cellulose and hemicellulose sugars that were broken down, and also lignin, which is a three-dimensional molecule that we'll talk about in a little while. Rice husk was then mixed, the lignin part of it was then mixed with standard binder and then put in asphalt mixes. And both of these were extensively tested. So that's kind of the overall idea of what we were doing. You can keep going. So approximately 94% of the roadway infrastructure is asphalt. All right, so that's a lot, really. And usually it's made from crude oil binder. The binders are made that way. It's kind of unsustainable and detrimental. Eventually, fossil fuel-based asphalt binders are going to be an issue because we're going to run out of fossil fuel. And then at that point, costs will rise up quite a bit. And so we're looking for viable alternatives that are more sustainable. And you can go on to the next one. So this is different things that people have suggested to replace asphalt binders. One is waste cooking oil by those studies that you see under the reference, and it had some positive things about it. However, you can make waste cooking oil into biodiesel, so there are other things you can do with it. Algae, it had some positive things, but it did tend to have phase separation if you put too much in. There's natural rubber and latex, and they had some positive things and some negative things, as you can see in the study by Wen. But natural rubber is eventually going to be a problem in our world. The fungus that killed off the rubber trees in South America will eventually probably migrate to Eastern Asia, where rubber trees make latex now. And so that's going to eventually be a problem. Biochar has also been suggested, and it has its advantages. Cellulose-based fibers also might be useful, as you can see. However, cellulose you can use for a lot of different things, like paper. Really tiny charcoal ash from coconut shells also had kind of, a good impact on properties of binder. But we're mostly interested in lignin. The study by Arafat et al. Was actually done at Louisiana Tech with Dr. Waziuddin and his student and me. And so we were kind of one of the initial papers that actually said, look, you can do this with lignin. So you can go on the next one. All right. Now, lignin is the second most abundant form of biomass. Now, biomass is just plants, pretty much. All right, so it's the second most abundant form on Earth after cellulose that you make paper out of. And about 50 million tons of lignin are generated from pulp and paper industry. The thing about that is much of this lignin becomes what they call black liquor, and they burn it in their own facility. So it's not necessarily available for us to be using it. And rice husk is another pretty abundant source of lignin. You can see how many million tons of rice husk are generated annually because rice is grown around the world. It's the second biggest crop after corn. So we were thinking about how can we feasibly produce lignin from rice husks, and what will happen if we put them in as a binder in asphalt pavement. All right, we can go on the next one. Okay, so this is the three major steps. You can see at the picture on the left, that's what it looks like after we do hydrothermal carbonization on it. But there are three steps: pretreatment, extraction, and purification. And the pretreatment can be physical, chemical. Oh, is there a laser pointer? Oh, that's nice. but I can't point with it. That's okay though. Um, so you can use acids or bases. You can use physiochemical like steam explosion. So basically you put it and then you change the pressure, suddenly explodes the biomass so that the lignin can be separated. And finally, biological ones. White rot fungi actually can dissolve lignin, but it takes a long time if you do the biological methods. So typically chemical methods are more used, especially in pulp and paper. You can also do things like organosolve, other hydrothermal processes, acids and bases, and ionic liquids, which I worked with some to make lignin, but the lignin's going to have different properties. Okay. All right. So we're excited about hydrothermal carbonization in my lab, obviously. It's just uses water and biomass. So that makes it simpler than many kinds of chemical pretreatments. And it can take out the cellulose, changing it, as I mentioned before, into glucose, because cellulose is just a bunch of glucoses all lined up. Or hemicellulose, it has different sugars in it too. So you get sugar water out of it, and then you have your lignin, but it doesn't tend to break the bonds, especially the beta O4 bonds in lignin, which you can see in the chemical structure on the right. Lignin is pretty much a bunch of benzene rings that are connected in different ways to other benzene rings in a three-dimensional matrix. So that's pretty much what lignin is looking like. If you want to go to the next slide. And these are some references of different studies that have been done. As you can see, most of these studies are very recent, most of them since 2020 or so. And so there were possible things, and the lignin had different effects on asphalt binders. Most of these studies, however, were from wood. And so we're kind of excited that we are using rice husks instead. Nice thing about rice husks is they aren't really useful for anything. They either get burned in the open field wherever they're produced, or else they get landfilled. Animals won't eat them. Okay, so they're not really useful for anything else. So they're a real kind of a waste, and a large quantity waste. You can go on the next slide, Dr. Ali. And this is just another idea about what has gone on. The paper that you see at the top is the one that we did here at Louisiana Tech, putting black liquor lignin in asphalt. We changed it so that we purified it, and then we put it in there, and we did find some good results for that. You can see Perez et al. In 2019, 20% lignin they put in their asphalt binder, and it was pretty good for a while, but then the benefits tended to go away after time, although they did get improved binder aggregate bonding. So that was one thing. If you look at the Gadenzi study on the bottom right, it was mostly wood that they used, and they did find increased indirect tensile strength, but they kind of had problems with when they went to different temperatures because it affected the cracking performance. If you look at 7 o'clock on this circle, you see that they used calcium lignosulfonate powder. That's something you could probably get from black liquor. So it's another wood-based one. And they found better stiffness and enhanced rutting resistance. Then finally, if you look at Zahedi et al. In their 2020 study, they did get, with a small amount of lignin replacing the regular standard binder, they did get improved Marshall stability and rutting resistance. But eventually, if you had too much, you had lower life. Okay, so let's go on to this. Rheological properties are going to depend on what kind of lignin you have. There are actually 3 different kinds of lignins, known as G, S, and H. And actually wood, like softwood, that is typically used in pulp and paper mills, it mostly has G-type lignin. the kind of rice husks that we have a mixture of all three types. So they're kind of different. And it just depends what the lignin monomer looks like that's predominant in the biomass. So as some of these studies mention, storage stability can be a major concern. You can have phase separation after you've mixed in the binder. Some lignin types are going to have poor compatibility. There's mostly been lignin modified binder studies with just characterizing the binder, but there's been limited attention to asphalt mix performance, actually putting it in an asphalt mix. So we wanted to study the whole gamut, starting from how we got the lignin to what happened when it was in the binder to what happened when it was in the asphalt mix. So that was what we were excited about studying. So we can go on the next slide. All right, so we wanted to do HTC to extract lignin. We wanted to look at the rheological properties and the mixes, just as I said before. The picture you see is that on the left is what rice husks look like when they're not treated. And then on the right, you can see what it looks like after they're treated by hydrothermal carbonization. So we can go on to the next slide. And this is what our research methodology looks like. We pre-treated it. We chose hydrothermal carbonization, a temperature at 250 degrees C. One thing I want to mention that at that point, you have the water that's in there with the biomass, and it has more H plus ions and also more H3O plus, or OH minus ions and H3 plus ions. And so that makes it a different kind of solvent than standard water. And the reason that is because this is water at 250 degrees C, which is way above the boiling point, and it's also high pressure. And so that's why you still have liquid water in the process. Then we characterized what lignin we got out of it. We looked at the lignin content, how much lignin we got out of it. We looked at the fuel value of it. We did some FTIR, or Fourier transform infrared spectroscopy on it. We checked on the cellulose content and the carbon content. Finally, we replaced either 5 or 10% of the asphalt binder with lignin. And we did a lot of testing, high, low, and intermediate grading, MSCR, master curve, storage stability, and that sort of testing. And we did rutting, cracking, and moisture-induced damage testing. And this, Dr. Ali is going to talk more about. So we can go on. So this is kind of what it looks like, the process. We add water to rice husks with 10 times as much water as the rice husks. Okay, so we weigh it, we put it in a glass liner. We put the glass liner in our reactor, which you can see on the top right. You can see some of my students doing it. So that's what the PAR reactor looks like. It's a 2-liter reactor that we use. It has a stir and it has a controller to make it go to a particular temperature. It also has a pressure gauge to see what kind of pressures we're ending up with. We then add the heater. There's a heating jacket that goes around the reactor to heat it up to 250 degrees C. And on the bottom left, you can see the controller. So that's what's happening in that picture. We can go on to the next one. Do what is called fiber analysis. Fiber analysis basically figures out how much cellulose do we have in our biomass, how much lignin do we have in our biomass. That's kind of what it does. And it's a protocol from the National Renewable Energy Lab. So first we take our product, our solid product. We add 3 milliliters of sulfuric acid to 0.3 grams of it. We then take put it into a 30°C hydrolysis bath for 1 hour. We then autoclave it in our autoclave at 121 degrees C for 1 hour. We then just weigh how much solid we have. The solid that we get is called acid insoluble lignin, okay, AIL. And that's because we put it in the acid and it did not dissolve. So it's the acid insoluble lignin. And then finally, we take the liquid that was there and we analyze it with UV spectroscopy for acid soluble lignin. So it's the stuff that dissolved out. So that's how we are characterizing our lignin. And we also, yep, you can go on. Thank you. We then did Fourier transform infrared spectroscopy of it, which can be a little bit hard to figure out, well, gee, there's a squiggly line. How do you analyze this? How we analyze it is we figure out the lignin to cellulose ratio. So at 1515, that particular peak, if you take the area of it, you can then divide that by the areas of a number of other peaks and that will give you what kind of lignin to cellulose ratio you get. So that's how we analyzed it. The untreated one is the green one. The treated one is the blue curve. And so we calculated those things and we found that in rice husks, if you don't treat them, the lignin to cellulose ratio is about 0.4. All right, but if you do treat it, you get about a 0.95 lignin to cellulose ratio. So it proved basically that we took out the cellulose from these rice husks. So we can go on to the next one. All right, and you can see if you look at we mesh these things to figure out what particle size we have. You can see that before we did hydrothermal carbonization, we tended to have pretty big pieces of solid, but afterward, we mostly had smaller particle size pieces of lignin. Okay, so that's kind of what it's looking like. We're talking about, let's see, 0.4 millimeters to 0.2 millimeters was the main area. So it's all about around, I don't know, 0.5 millimeter after you've done hydrothermal carbonization on it. Good. We can go on the next one. There we go. And we also checked some other things that would be of interest. We looked at the fuel value, essentially, of it, and that did not change a whole lot with hydrothermal carbonization. We looked at the cellulose and hemicellulose concentration before and after, and we saw that we had way lower amounts of cellulose in it. So 84% reduction in cellulose for the biomass. Our bulk density also went up, so you could put more into a truck, a higher weight of it into a truck after you had done the HTC to it. And we also got greater elemental carbon. So we can go on the next one. And you can see that the rice husk, also the acid insoluble lignin went up, and we had a lignin yield of about 60%. So that's what happened when we did hydrothermal carbonization on it. And we can go on the next one. And we also had to do a particle size reduction. So we took the stuff right from the reactor after we filtered it. We stored it in the refrigerator for 2 hours. Then we just put it in a plastic bag and hammered it. And doing that, we were able to make it all pass a number 80 sieve. So it was all smaller than 0.18 micron, or 180 microns, but most of it was bigger than 75 microns. So we kind of had a small particle size. And those are the laser scanning confocal microscopy images. So you can see that they're at the same scale, so you can see that the particle size went down. That's pretty much the story with that. We can go on to the next one. And we also checked the melting point of lignin and found that it was around 260 degrees C. Those are 3 different runs when we did differential scanning calorimetry. And so basically, since the melting point is pretty high, it's not melting when we're mixing it into the binder at 170 degrees C. So pretty much it's staying as a particle, it's not melting. And we can go on the next slide. And I'm going to turn it over to Dr. Ali, because he's very eager to talk about the experimental plan. Except his microphone is off.
Yeah, it looks like you're still muted.
I'm sorry about that. Yeah, yeah, I could not see. So let me get back. Is it okay now?
Yep, perfect.
Okay. Thank you. Thank you, Dr. Lynam, for giving us a very good overview of how lignins are produced, right? So now we are going to the application part of it, how we can add lignin to asphalt binder and how we can use it towards asphalt mix and how it is going to impact the performance and properties of our asphalt binder and asphalt mix. So we kind of had a very comprehensive testing approach that we tried. And as you have seen, 3 universities are involved in this. One is Louisiana Tech University, who were the lead. They did most of the asphalt binder testing. Then Louisiana State and and the University of Oklahoma, we both evaluated the properties of the asphalt mix. So to begin with, to evaluate to modify our asphalt binder with lignin rice husk derived lignin, we collected a commonly used PG67-22 binder. I know people from Oklahoma does not recognize this because we do not have a PG67 grade, but it's common in Louisiana, and they choose to have a very commonly used Louisiana PG67-22 binder. So we get that, and we wanted to modify that binder with 5% and 10% lignin. So the way it worked is that we wanted to replace 5% lignin or 10% weight of the binder and add this 5% and 10% lignin to it. If we wanted to make a 100 gram lignin, 100 gram asphalt binder, modified asphalt binder, we took 95 gram of asphalt binder, and that rest 5 gram was lignin. So that's how we worked. So at the same time, when we were doing the 5% and 10% modification, we also did some other things as well. We did a 10% lignin modification with 1% styrene butadiene styrene or SBS modification. We also did prepare another binder, modified binder with reduced size lignin at 5%, and also another binder with a modified binder with a reduced size 5% lignin with 1% styrene butadiene styrene. The purpose of using styrene butadiene styrene and also the reduced size lignin, as Dr. Lynam was explaining how we got that reduced size lignin, it was to see whether we can use those products to improve the storage stability of lignin modified asphalt binder. Okay, so we have developed a testing protocol to mix lignin with asphalt binder, and I'm going to show you in our next slide how we did it. And when that product is ready, we use the unaged lignin modified binder, and we evaluated the high temperature performance grade using dynamic shear rheometer or DSR testing. We conducted MASCAR or MSCR test, multiple stress free recovery, and also we evaluated the storage stability test, conducted a storage stability test on the modified binder. Then we conducted a short-term and long-term aging through short-term and long-term aging protocol. We got the through the RTF and PAVS sample. We have done the DSR testing again on the RTFS sample to find out the high temperature performance grade. And on the PAVS sample, which represents the long-term aging, we used the BBR test, bending beam rheometer test, to find out the low temperature properties. And also we conducted the rheological master curve to find out the difference between the need binder and the lignin modified binder. And then overall, we try to understand from the whole testing, whole results, we try to understand how the rheological property has been impacted by the addition of lignin. Okay, so this slide actually shows us the mixing procedure that Louisiana Tech has used, developed and used for this product. So it shows that at the beginning, obviously, we have to have a liquid asphalt binder. So we heated up the asphalt binder at 170 degrees Celsius. Then we measured the amount of lignin that we need for this purpose. And then we started adding that lignin into the asphalt binder and mix it using a shear mixer. So during the shear mixing, we use, you can see this is the high shear mixer that we have used for this purpose. The mixing speed we maintained, initially we started with 4,000 RPM for the first 30 minutes, and then we increased that speed to 8,000 RPM for the next 20 minutes to make sure there is a continuous and uniform mixing of lignin within asphalt binder. And during the mixing procedure, we try to maintain the temperature between 160 degrees Celsius to 170 degrees Celsius. As you can see, we were continuously monitoring the temperature at so that like it doesn't go below or after or above that range. So through this process, we were able to produce the lignin that we need, 5% lignin, 10% lignin. That's the two we wanted. And also we used the similar procedure when we added the SBS, styrene, butadiene, styrene. Okay, here is the results for the DSR test, dynamic shear rheometer test at high temperature. So the parameter that we wanted to look at from this DSR was G star over sine delta. So G star over sine delta is generally used for as an indicator of rotting resistance. So what we did, we conducted the test on PG67-22, then 5% lignin modified and 10% lignin modified binder at 70, 76, and 82 degrees Celsius. As you can easily see from this graph, is that with the addition of lignin, 5% and 10%, we have seen an increase in the G star over sine delta value. And this trend is true for all temperatures, 70, 76, and 82 degrees. So it tells us that the rotting resistance of asphalt binder is going to improve with the addition of lignin. So we can expect some good rotting resistance with the higher amount of lignin. At the same time, we try to identify or find out how much impact lignin could have on the high temperature continuous performance grade. For PG67-22 binder, the continuous performance grade was 69.3 degrees Celsius. With the addition of 5% lignin, it increased to 70.9 degree. And when we added 10% lignin, it increased to 71.4. So we can expect around 2 to 3 degrees Celsius increase with 10% lignin. But with 5%, not much, maybe 1 degree, 1.5 degree Celsius increase with 5% lignin. Then we also, as I have mentioned, we wanted to see how lignin will impact the low temperature performance grade. We conducted the bending beam rheometer and find out two parameters that we get from bending beam rheometer testing. One is called the stiffness or S value. Another one is the M value or the stress relaxation, right? So we stress stiffness and stress relaxation. We conducted the test on the lignin modified neat and lignin modified binder at -6, -12, and -18 degrees Celsius. And we found out with the addition of lignin, the stiffness increases significantly. And with temperature, obviously, as we go the lower temperature, we have seen an increase in the stiffness value significantly. For M value, with the addition of lignin, we have seen a decrease in the AM value. So what does it mean? We are seeing that at low temperature, the stiffness will go high if we have higher amount of lignin, but the stress relaxation will suffer if we add higher amount of lignin, right? And so that could be a problem for low temperature cracking. So low temperature cracking resistance wise, that could be an issue with the addition of high amount of lignin. So we have to keep that in mind. We wanted to see how the amount of lignin impact the low temperature performance grading. As you can see, uh, initially the PG67-22 binder had a continuous grade of -23.2. After the addition of 5% lignin, it didn't change much. It's still a -22 binder with a continuous grade of -22.9. And when we added 10% lignin, that changed quite a bit. So with the addition of 10% lignin, it went down to -20 degrees Celsius. So around 3 to 4 degrees Celsius change in the low temperature grade. So that also indicates that low temperature cracking or the use of this asphalt binder at low temperature may be an issue. Okay, so as we have seen, the 5% lignin is not showing much difference both on the high end and also on the low end. So we wanted to do this develop this rheological master curve, do the testing at different frequencies, and and try to understand, is there actually a difference between the neat binder and the 5% lignin modified binder at broader spectrum, okay, at different frequency, and obviously frequency can be converted to temperature as well through some superposition principle and stuff. And so what we have found that if we use the complex modulus G star value at different angular frequency for PG67-22 and PG67-22 at 5% lignin, they're almost same. There is not much difference between these two at the higher frequency and also at the lower frequency as well. So we can expect that, and also we have seen the same thing for storage modulus, loss modulus, and also for phase angle as well. So the master curve is actually showing that the 5% lignin modification did not significantly change the rheological behavior across broad temperature range or broad frequency. Okay. So we did a mascate test or multiple stress creep recovery test on a lignin modified binder. The two parameter that we looked at from the mascate test was a JNR or non-recoverable creep compliance, and another one was percent recovery. So generally, percent recovery indicates the binder's ability to return after deformation. This is the elastic property. It represents the elastic property of the asphalt binder. And we found that although lignin not a polymer modified, it increased the recovery a little bit, not much. Okay, we can expect some recovery, higher amount of recovery than the neat binder, but as lignin is not a polymer product, so it did not impact the percent recovery that much. JNR on the other hand represents the rotting resistance under cyclic loading. A JNR value of lower is better, right? So we have found that with the addition of 5% and 10% lignin, the JNR value goes down significantly, and it also indicates that the rotting resistance will improve with the addition of lignin. So this is one important thing that we wanted to see what is the impact of lignin on the storage stability, because we have seen several research that shows that reported that the storage stability could be an issue when we want to use lignin. So we did a test called Seeger tube test using ASTM D7173 standard. In this test method, we have used a Seeger tube, that is a Seeger tube, and then we filled that Seeger tube with asphalt binder, and then we put it into oven at 163 degrees Celsius for 48 hours. Then we took it out and directly put it into the freezer at -18 degrees Celsius for 4 hours. So after these 4 hours, we took the Seeger tube out, divided into mark it at three equal division, and then cut those cut that cigar tube into three parts. And then we conducted the DSR test on both this top part and also on the bottom part. So from the dynamic modulus test, sorry, not the dynamic modulus, dynamic shear rheometer DSR test, we find out the G star value for the top and bottom, and then use the ratio of G star of the top and bottom sample as a stability index. This index was then used for the comparison purpose. An index value of 1 will indicate that the thermal stability or the storage stability of the material, and also it will indicate that it has a better uniformly mixing of the binder and lignin into the binder. So stability wise, this is this graph here shows the stability index of lignin modified binder. So when we added 10% lignin, the ratio of G star of the top and bottom sample, it went down very low. We found around on an average 0.46 stability index of 0.46, which indicates a very poor stability. That means with the addition of 10% lignin, we can expect phase separation, and it will be difficult to get a uniform lignin modified binder. But with 5%, we see that there is some improvement on the storage stability around 0.67 to 0.68. But still, this is not enough. This is not very close to 1. So what can be done in that with that respect? So we have taken two approaches. One is to reduce the particle size of the lignin that Dr. Lynam has already described. So we reduce the particle size, and we added those reduced particle sized lignin to the asphalt binder, and we found that it improved the storage stability by quite some degree, around like 0.76 from 0.68 to 0.76. But again, we wanted to improve it more and wanted to find out what can be done to improve it. So we added SBS, 1% SBS, styrene butadiene styrene copolymer to our asphalt binder, and found out that using SBS significantly improved the storage stability. So that is one of the recommendations that we have from our this project, is that in order to make sure that we have a good storage stability, we may have to use some other type of additives or polymer to improve the storage stability of the lignin modified binder. For 10% lignin modification, though, as like with 10%, the value, the storage stability goes down so much that it is even difficult to get it back to the level that we want with the addition of SBS modification. So yeah, but 5% did pretty good job. Okay, so that was the end of the characterization of asphalt binder. As I have already mentioned, Louisiana State University and the University of Oklahoma, we took over and did the asphalt mix testing. And all these works were going parallelly, because Louisiana State was working on asphalt binder, properties of the asphalt binder, and Louisiana State and University of Oklahoma was working on the asphalt mix. And Louisiana Tech produced the asphalt binder, and they shipped it to LSU and OU to do the asphalt mix testing. So after we got that asphalt binder, Louisiana wanted to use that asphalt binder to produce a asphalt mix with nominal maximum aggregate size of 12.5 millimeter. The control mix that they selected, that was already an approved Louisiana Department of Transportation and Development, the LADOT asphalt mix. So it was already approved, and it was already been used on the pavement. So they use that as a control mix, and they just replace that asphalt binder with this lignin modified asphalt binder from Louisiana Tech. The aggregate that was used, you can see the different aggregates that was used on this asphalt mix. I want to keep your attention to the RAP portion of it. So this mix already had 19% RAP, and it obviously had some impact on the mix performance as well. The amount of asphalt binder used for this to produce these asphalt mixes were 4.6%. Around 1% of the asphalt binder was expected to come from RAP. And here is the aggregate gradation that was used by LSU to produce this asphalt mix. Similarly, Oklahoma at University of Oklahoma, we also selected a asphalt mix, an asphalt mix that was already been done before, and it had a nominal maximum aggregate size of 12.5 millimeter. The amount of asphalt binder we used was 5.2%, and these are the aggregate that we have used. Again, this mix also had around 20% RAP in it. Okay. So the way we during the addition of asphalt mix, during the when we use the when we add asphalt mix to our aggregate, the way we did it, we calculated the amount of asphalt binder we need is the amount of asphalt binder was adjusted to incorporate 5% and 10% lignin in the asphalt mix. So we had to adjust this 5.2% and make sure the whole asphalt binder is 5.2%, where probably 4.9% is the real is the new asphalt binder. 4.9% is the asphalt binder, and the rest portion is lignin. It came from the lignin. So used lignin as a replacement of asphalt binder. So at Oklahoma, also we tried another thing. We have seen some issue with on the performance of lignin modified binder. So we wanted to see whether use of rejuvenator can help improve some of the properties that were that we had some issue with. So we used a 2.1% rejuvenator on the 10% lignin modified asphalt binder, asphalt mixes. Okay, here is the asphalt mix with the lignin modifiers. This is the process we used. We batched the aggregate, and then we although the asphalt binder was already mixed with the lignin, but before mixing this asphalt binder, before putting this asphalt binder in our aggregate, we wanted to make sure the lignin is suspended properly and it is uniformly distributed. So we did mix for 2-3 minutes using as you can see drill here. We made sure that the lignin is suspended on the asphalt binder, and then after we do that, after we use this agitated asphalt binder, modified asphalt binder in producing the asphalt mix, and this is the loose mix as you can see, and then we compacted the asphalt mix and compacted the asphalt and used for rotting, cracking, and moisture-induced damage evaluation. For rotting, we used Hamburg wheel tracking test, 150 millimeter diameter sample with 62 millimeter height. Test was done at 50 degrees Celsius, and the wheel pass frequency was 52 pass per minute. We used ASTO method, where we looked at the rot depth at different cycles and also the stripping inflection point for moisture-induced damage. Texas A&M or TAMU method, this is another method that is getting popular by many DOTs and many agencies. So we wanted to use that too. Using this method, the viscoplastic strain and the stripping strain was separated, and then also we used 3 different parameters. One is called the viscoplastic strain at the stripping number that was used to evaluate the rotting. The stripping number was used as a indicator of moisture-induced damage, and also the stripping life was used as an indicator of moisture-induced damage. By the way, this test was done only on the Oklahoma mix. We kind of like separated. Oklahoma did evaluate some property. LSU evaluated some other properties of asphalt mixes. We wanted to see how the lignin modified binder will impact the cracking resistance. The test we used for that purpose was ideal CT. ASTM D8225 method was used. We calculated after doing the test, we calculated the CT index value of the asphalt mixes using this formula. And I'm not going into the details of this formula here. We'll talk about more on the results. We also evaluated the moisture-induced damage characteristic of the asphalt mix is using tensile strength ratio or TSR testing. TSR using the ASHTO T283, 100. We prepared a 150 millimeter diameter sample with a height of 95 millimeter. We use a 3 for dry conditioning, 3 for wet conditioning. The wet conditioning was done using a 1 freezing and 1 thawing cycle. So after doing the test, after determining the indirect tensile strength of the asphalt mix, we compared the strength at the wet condition over dry condition. And this was done only on the Louisiana asphalt mix. So here are the results of our asphalt mix that we did, testing we did. The rotting resistance of the asphalt mix, as you can see, this is the 4 mixes that we evaluated at the University of Oklahoma. 0%, 5% lignin, 10% lignin, and 10% lignin with 2.1% rejuvenated. So we have seen that the 5% lignin actually did a pretty good job. It didn't show any stripping slope, but the 10% lignin with 2.1% rejuvenator showed pretty significant stripping, and also 10% lignin had some stripping shown from the rotting test. So let's look at the results. We use this data to analyze the rotting resistance different parameter from here. The ODOT requirement for good rotting resistance is less than 12.5 millimeter or less than ½ inch after 10,000 wheel pass if the asphalt binder is PC64 minus 22. So if we looked at 10,000 wheel rot depth at 10,000 passes, all of the mix showed very good results. All of them 5%. But at the same time, if we look closely, with the increase in lignin modification, we see that the rot depth goes down. For 5%, it was 5 millimeter. For 10%, it was 4.17 millimeter. And also, we have seen almost the same thing for 10,000, 15,000, and other 20,000 wheel passes as well. So we can expect to have a significant rotting resistance from lignin modification of our asphalt mix. Rejuvenator produced the rejuvenated mix with 10% lignin also produced almost similar results until 10,000, but after that we have seen some significant increase in the rotting. So that could be an issue with 10% lignin with rejuvenator. And in stripping inflection, if we look at the stripping inflection point to understand the moisture resistance of this mix, all this mix did a pretty good job. They showed a very high stripping inflection point. The 5% lignin was more than 20,000. The 10% lignin was almost like 16,000 wheel pass. And the 10% lignin with 2.1% rejuvenator was around 14,000 wheel pass. So moisture induced damage wise, most of the all the mixes did pretty good. If we analyze the result using TAMU method, where there are 3 parameters that we wanted to see. One is the viscoplastic strain at the stripping number. A lower value is good. So we have seen with 0% lignin, it was 4.97 times 10 to the power minus 6, whereas at 5% lignin, it goes down a little bit. The 10% lignin, we could not calculate. The software that we are using, it was giving some error, so we could not calculate that. And then 10% lignin with 2.1%, it increased the viscoplastic strain number. So it shows that we can the rotting may go higher with the use of rejuvenator. But stripping number wise, we have found it's pretty good. Stripping number, higher stripping number shows less possibility of or less susceptibility to moisture. So we have seen pretty good with the addition of lignin. We have seen pretty good stripping number, increase in stripping number, and also stripping life shows good indicates good moisture resistance of the lignin modified asphalt binder. Cracking resistance. So what we have seen on the cracking resistance. So these are the 4 different. We took 4 different samples. Load displacement curve for cracking resistance. The first one is for 0% lignin, the control mix. Then the B is for 5% lignin, C is for 10% lignin, and D is for 10% lignin with 2.1% rejuvenator. What happened with the addition of lignin is that the ultimate load to failure increased significantly. For example, at control, it was around like 15 kilonewton, whereas with the addition of 5% lignin, it went over 20 kilonewton. And then at the same time, we have seen almost the same number for 10% lignin modification. And obviously, with the addition of rejuvenator, that it softened the asphalt mix, and the ultimate load to failure went down. Also, at the same time, if you closely look at the post-peak slope, which indicates whether the material is ductile or brittle, we have seen that the slope become more and more steep. As a result, we can expect to have a more brittle behavior of asphalt mixes with the addition of higher amount of lignin. And we have so here are the results for the indirect tensile strength that we have calculated from the same test, the ideal city testing. We have seen that for 0% lignin, the ITS value or the indirect tensile strength was pretty low, but with 5% and 10%, it went up very high. And with 10% lignin with 2.1% rejuvenator, it came down a little bit with the addition of rejuvenator. But an increase in stiffness of the asphalt mix is actually responsible for the increase in the ITS value. Also, we wanted to look at the failure energy and also the post-peak slope of the asphalt mixes. The failure energy we have found to increase with the lignin content, and also the post-peak slope also increased with the lignin content. As I was mentioning, the mix is getting, the post-peak slope is getting steeper. So as a result, it may be more stiffer and more brittle mix. Lignin is with the addition of lignin. So what it is doing to the CT index or the cracking resistance. So this is one of the things that we have found, that with the addition of lignin, as the lignin amount goes high, we have found that the CT index value goes down significantly. Although between 0% and 5%, because of the variability of the results, they may not be significantly different, but with the addition of 10%, it went down pretty significantly. And so our idea to add rejuvenator was to see whether adding rejuvenator can increase the CT index value. But we have seen that although the mix is not as stiff as the 10% lignin, but the addition of rejuvenator did not help much in increasing the CT index or cracking resistance. So we have seen almost the same similar type of result from Louisiana asphalt mix as well. So they also did the CT index test on the control 5% lignin and 10% lignin mix. So the control mix showed the highest CT index value. The 5% and 10% lignin showed the lowest, but if we look closely, the statistical analysis showed that they are not actually significantly different. So 5% and 10%, there is no significantly different CT index values. So what happened here? So we asked ourselves what actually happened, and so that the CT index value went down. The one was that we have used a pretty high amount of RAP and also at the same time lignin. So 20% RAP with lignin, that could have been a problem that we have seen this low CT index value. And also at the same time, we have used unmodified binder. So if we have used a modified binder or SBS modified, some amount of SBS modification, that could have helped. But this was a 1-year project, so we could not explore much. But we are planning to extend this work and explore our other options so that we can get a improved cracking resistance from our mix. Tensile strength ratio of asphalt mixes. So tensile strength, we have seen significant improvement of the tensile strength with the addition of lignin, 5% lignin. But the 10% lignin, or the TSR value went down a little bit. So we can expect that the 5% lignin performed pretty adequately and slightly better than the control mix. So this is one of the positive things that we have seen from with the addition of lignin. So what are our conclusion from this study? So collaboratively, we did a lot of work. We tried to look at the lignin production. We tried to look at the binder part of it. And also we did characterize the asphalt mix performances as well. We have found that the HTC process can be used with a 250 degrees Celsius temperature, can be used to extract lignin efficiently. And then we can use it for modification of our binder and use it in our asphalt mix or asphalt pavement. Lignin improved the rotting resistance, resulting in an around 2 degrees Celsius increase in the high temperature performance grade. If we use 10%, but if we use 5%, we may not see that much increase. We may see around 1 degree to 1.5 degree increase in our performance grade with 5% lignin. Mascot test and also other tests have showed that the rotting resistance with lignin modification will be improved significantly. Low temperature cracking resistance could be a problem, but we have seen with 5% it is still okay. But when we go for the 10%, the high amount of lignin, it goes down significantly. 10% lignin was found to be unstable. We may need to do a continuous stirring before to improve the stability of 10% lignin. And we have found that the use of SBS modification can significantly improve the stability. So that will be our next target to see whether we can use this process addition of SBS to improve the lignin modification. Satisfactory moisture-induced damage resistance were observed from resistance was observed from the asphalt mixes with lignin modified binder. Also, the rotting is good. ITS, indirect tensile strength, increased significantly with lignin. The cracking resistance went down a little bit. Cracking resistance went down with the lignin modification. So we can expect to have good moisture-induced damage resistance. We can expect to have good rotting resistance, but cracking resistance could be a problem. So what are our recommendations from this study? So we can expect that the lignin, we have seen that the lignin is actually acting as an asphalt extender. So minimum binder requirement can be reduced if we use lignin in our asphalt. And also fatigue performance will be the dominant governing factor for asphalt mix design. If we use lignin in using wet process, maybe during field construction, we have to have a mechanism to agitate the asphalt, that blended asphalt mix or modified asphalt, modified asphalt binder, so that like we have a uniform mix just before we add it, like mix it with our aggregate. But our recommendation is that we should use a hybrid process for design and construction. During design, we can use add lignin to the asphalt binder, modify the asphalt binder, and do the design. But when we want to use it in the field, we can use it using the dry process. Use it through the wrap port. If we add lignin through the wrap port and have our asphalt binder come through separately and then do the mixing, that could be one way to do they get away with this agitation and the storage stability problem. Future work is definitely needed to incorporate other types of binder and also with varying lignin content. So thank you all. Thank you very much. I think I went a little bit over probably, but if you have any question, I will be glad to take that questions. Thank you.
All right, thank you so much. A big round of virtual applause for Dr. Lynam and Dr. Ali. Great presentations. So if anyone has any questions, please feel free to post in the chat or raise your hand and unmute yourself. It does look like we do have one question in the chat. This one is from Safir Haider, who says, did you develop any acceptance criteria for lignin to use it in asphalt binder mixture? Because as lignin sources consist of different components, so variability will affect asphalt performance.
Yes, we've looked at a lot of different ones, but not in asphalt. So mostly we've done rice husk asphalt, which is going to have G, S, and H in it, all three, because most grassy biomass have a mixture of those three monomers in their lignin. The one study we did with black liquor, that we made the black liquor, we precipitated out lignin from black liquor. That would have been from softwood, which would mostly have G. So pretty much whatever area you're in and you want to try to put lignin in your asphalt and use hydrothermal carbonization, which can be done at high scales. Actually, cruise ships, believe it or not, do hydrothermal carbonization on their waste. And they have huge amounts of waste. And so it can be done on a large scale, but you're going to have to pick whatever biomass is that's a waste biomass that's in your area to do the to get lignin from. So it's going to be different for every area of the country. Good question. Thank you.
All right, thank you. Yes, we have a couple more questions. Ginger McGovern says, what would be the energy consumption of the HTC process at scale needed for highway construction? Does it save energy compared to just using AC binder?
We have not done an embodied energy study on this yet. So the thing about hydrothermal carbonization is that you do have to heat up the water and the biomass. But there have been studies where they figured out, well, if you heat it up, you can then use that heat to preheat the stuff coming in if you have a continuous process. So it actually is a little bit exothermic because you're hydrolyzing the cellulose. So you're breaking bonds, and the broken bonds are making energy. So it probably wouldn't be a terrible amount of energy you'd have to be adding to the process. Compared to pumping stuff out of the ground, transporting it, and making it so that it actually becomes nice asphalt binder, those processes would require energy as well.
All right,
Good
excellent.
question.
Thank you. We have another question posted in the chat, then I'll get to the two hands raised, and then we'll get back to the chat. Emerson Pollard asks question number 1, the use of lignin, is it ODOT approved?
Not yet. We're just doing research so far.
Yeah,
You're going to
so
say something, Dr. Ali?
Yeah, so yeah, the use of lignin is not ODOT approved yet. Yeah, so we are exploring options. We are exploring new things that yeah. So this is not ODOT approved yet, but hopefully at some point we'll get there that it could be approved. Thank you.
We're thinking 20 years in the future. I mean, this is not going to happen right away.
All right, we'll go to our first raised hand. Mehdi, it looks like you have your hand raised.
Hi, I'm Mehdi Hassan from Helitech. I'm new grad student here in Asphalt Material Labs. My question is, in your mix, Oklahoma mix design, you use 2.1% of rejuvenator. So why is that that percentage is fixed? My question is, can we vary the rejuvenator or it is fixed? That means why you use this percentage? That is my question.
Thank you. Thank you, Mehdi, for this question. This is a good question. So actually, the control mix that, as I have mentioned, it came from another mix design before, right? A previous mix design. So previous mix design that had 2.1% rejuvenator on it, and we did some study that time, and we have developed that control mix during that time. So we wanted to keep it consistent. We wanted to keep it to 2.1%. We have found that like for 20% wrap, 2.1% was needed. So we just explored that option. We did not. It could be varied, but we did not explore that because of the time and scope, resources limitation in this project. Hopefully, I answered your question.
Thank you.
Thank you.
Yes, thank you.
All right, great. We have another hand up with Emerson.
Hey, good afternoon. I've got a couple questions.
Sure.
First one is, well, actually, let me a little background on us. The company I work for, we actually produce the asphalt. So I'm thinking about longevity. We know that asphalt itself is perishable. So do we know if the use of the lignin, will it cause the asphalt to retain heat longer? And ultimately being a radius. So if I've got a 80-mile radius during the summertime because of temperatures, will that carry it any further? And our mix is virgin right now. So was any portion of this used on virgin mix?
Well, you want to answer the virgin mix one, Dr. Ali?
The virgin mix. If I understood it, so you want to know whether lignin could be used in virgin mix, right? And the temperature.
No, ultimately, we don't. I noticed that you use RAP, recycled asphalt products.
Yes,
We
yes.
don't use that. So my thinking is, and I could be wrong, my thinking ultimately is if we reduce some of the binder, we add some of that lignin, we'll be able to extend the life, so to speak. Because if it's carrying the heat, it's like almost like adding salt to water when you boil it. It has a higher boiling temperature. So if we're able to add that to the binder, are we able to carry the heat that much further? And do we know if it burns cleaner? Because I know that some people are thrown in almost like a like a fiber in the asphalt, and it on the back, and it almost gums up the works, and it's just detrimental to the bag house. So we just don't like to use that. So that's ultimately my. I'm looking to extend the life of the asphalt and save money ultimately.
No, sure. No, thank you. I think let me ask whether Ken, are you here? Ken Hobson?
Yes, I'm here.
I think you may be more qualified to answer this question than ourselves.
Okay. Ken Hobson here, University of Oklahoma, former ODOT asphalt engineer. My thinking is the wet process, it would be encapsulated. So like, if you can't associate this like ground tire rubber, the wet process, the dry process, or the hybrid process, which some ground tire rubber manufacturers are doing, you can use this product in the same similar way. So if you're using the wet process, then you have the problem of stability as discussed, but you wouldn't have any bag house issues. If you use the dry method as we proposed, like you do in ground tire rubber, you would have similar issues like you would have with ground tire rubber. So that's why a field project would be good to look at something like that. We proposed the hybrid process. That's what some ground tire rubbers are done. But certainly more research could be done to see, well, can we go all dry process in both the design and the field? And if you do it in the field, does that affect your bag house? That would certainly be something to look at.
Yeah.
So future study is needed.
Got it.
Is
Got
our
it. Thank
standard
you.
answer, right?
Good. And then, so then what about the portion about it, a sample, I don't know, maybe a ton of asphalt, adding it, metering it to a ton of asphalt, and then the checking the longevity of the temperature. Will it carry the temperature that much longer?
I don't think it'd be an issue. I think it'd just be the same as normal asphalt. It's black, as you saw in the carbonization. So black is going to absorb heat. And so the liquid asphalt binder is black, so that absorbs heat. So I don't think it'd be a factor.
One interesting comment I want to make is that what hydrothermal carbonization essentially does is the same thing as when crude oil is made, except faster. So it takes thousands of years to make crude oil out of essentially biomass underground, but hydrothermal carbonization just speeds up the process to 10 minutes or whatever. So it's kind of like, let's make crude oil but just doing it faster.
Okay.
Or asphalt, bitumen, just make it faster.
Okay. Right. Thank you.
Thank you.
All right. We have 1 minute left. Maybe time for one more rapid question. This time from Farouz. He asks, recently ODOT used an admixture to pave about 1 mile of road in Oklahoma County. Any info on this admixture?
Firoz, which one you were referring to? I'm not sure. I'm not sure whether they have used lignin on that project. I heard like yesterday or day before yesterday, they were using Kevlar fibers in one of the project in Tulsa, and not in Tulsa, in Lawton, I guess. So
I read in a paper a week or two ago.
Yes.
It was either in Lincoln, Oklahoma County, 1 mile. I guess, trial or whatever it was. And I remember that the name was start with K, but I can't remember the ex-speaker name.
Oh, okay. Yeah, I'm sorry. I don't know about that. And yeah, we are not also involved on that project. I'm sorry. Yeah.
Okay. Well, I got some ODOT connections. I can find out.
Sure. And let us know, please. Please let us know. Thank you.
I'm myself an ODOT old timer anyway, so I'll check into it. Thank you.
Thank you.
All right, we are at 3:15 Central Time. I want to be respectful of our presenters' time as well. So if it's okay, is it all right if people email you afterwards if they have any other questions?
Sure. I'm quickly writing my email address down. So if any questions, please reach out to us.
Perfect, thank you. And as our presenters are putting their emails in the chat, just a reminder, we will be sending out PDH certificates for everyone if you want one. And we'll also be sending out a survey. So please do respond to that survey. Helps us provide more topics and webinars in the future. So again, a big round of virtual applause for our presenters for doing a fantastic job. Many thanks. And we look forward to seeing everyone the next time we do a webinar. So thank you again. Hope everyone has a good rest of your day.
Thank you. Thank you, everyone.
Pleasure to talk with you. Thank you.